Physical science time. Today we are talking about energy. Today we are mathing about energy. Oh, my little lights. Well, we're going to do it. We're doing it without lights today. I wrote down what my class goal was, but maybe my actual goal should be to say less. That was almost it already. Energy. Define energy. You should remember this from last year because I remember it from last week. I've taught this probably 25 times in this school building. I know what the definition is, and I think you should too, because one of those times it was to you last year. Please define energy for me. It doesn't have to be perfect, and I don't want it to be perfect because I don't want you to read it right out of your vocabulary, although I'm glad you did your vocabulary. It's good that you know these words. But in your own words.
Power.
Okay, so let's relate it to power. What else? Is it only power? I mean, I know what you mean, which is that in the way that we use energy in our daily usage and the way that we use power in our daily usage, they're kind of interchangeable almost. Because you might be considering this kind of power, like the power that powers these lights. And that is energy, because you might equate energy and electricity and power. And those are different concepts scientifically, but they're not unrelated. And so we have here a question of power. What else? I like that. I'm not going to write down everything because you might say something really out of pocket. No, not probably stupid. There's no such thing as a stupid question. Only stupid people who ask questions. I'm just kidding. That's not how the phrase actually goes, I don't think. What else? The goal is not actually to say unless. The goal is to relate your labs better to the objective. The objective, analyze and interpret data from a model of energy transformation. And in your lab, did you model, I hope you did you model energy? Yep. In fact, you can't help it. Every time you've ever done a lab, every time you've ever eaten cereal, every time you've ever planted a garden, everything you've done in your life is about energy. But this lab was specifically designed, hopefully, to be about an energy transformation. Why don't you tell me? Ada, you were trying to say something and then you got exasperated and stopped because I was still talking. Why don't you tell me what you're going to say? Okay, so we have some examples here. I'm going to put the examples over in this, and we are going to keep this up. So we have examples, and I'm going to break them up, as I did for the 8th graders last week, in this way. We have two main types of energy, kinetic and potential, which we will both define and expand the list from those. Great. In your lab, in y'all's labs, you demonstrated kinetic and potential energy. What else could we say about energy from our labs? It can be thermal energy. Let's put that in here somewhere. Do you think thermal energy is kinetic or potential? It's both, yeah. Okay, chemical energy, do you think that's kinetic or potential? Yeah, you could probably make a case for both, but I'm going to put it firmly in the camp of potential. Now that I've done this one kind of chaotically in the middle, it seems like maybe a Venn diagram might have been better, but kinetic and potential energy as two kind of separate but not exclusive categories. Okay, the question what's that? The question we're still trying to visit is, what is energy at all? And sometimes to list examples of something is a good way to help define it, to orbit the truth of it. Excuse me. Okay. Helps something move. I like where this might go, which is that how did we define motion? No. Maybe go back in your notes. Thank you, Avery. How do we define motion back when we talked about motion? There we go. A change in position. That's really important. Energy always has to do with a change. That is important. Has anything ever changed in your life? Yeah. Yeah. Have you ever watched in a microwave as a little puddle of egg changed into a cooked egg? You've never microwaved an egg? What's something a normal person microwaves? Popcorn. Have you ever watched in a microwave? Hard for me to relate to you normal people because you don't cook eggs in the microwave. Have you ever watched in the microwave as flat, nasty, worthless bag of popcorn becomes big, fluffy, beautiful bag of popcorn? That's a change, isn't it? So was energy involved in that change, and how can you tell?
Yeah, thermal energy.
Okay, not only that, but yes, thermal energy.
Chemical energy.
One thing I love about... Yes, that's right. Okay, chemical energy and thermal energy. Is anything else going on? Can you bring your microwave with you to the camps? Well, you guys might have a different kind of campsite. Could you bring your microwave with you into the wild and make your microwave popcorn that way? Why not? What's not there? Electrical. And so is electrical a kind of energy? And what do you think, kinetic or potential? Yeah, I'm amazed you all got that right. Because I would have thought it was the other way if I didn't know things, which you don't. You know what I'm doing is every time I think that I say a funny joke and no one laughs at it, I say the word and so maybe that's the problem. The goal, as I was talking about, is to better relate your labs. So did anyone's lab have changes in them?
Yeah.
Did anyone's lab have changes in? Let's go through the list. What changed in your lab? You, I don't know, y'all. Yeah, didn't you have one group? Okay, so the potential energy changed to kinetic energy, so that's kind of a change of change. How did you see the object changing? Yeah, it bounced. In your lab, an object was dropped and it bounced and it went back up, but only part way. Okay, and we talked about this, and actually, I'm going to draw this example. Nope. The ball is in the process of dropping, and then it bounces back up to maybe here, and then it's in the process of dropping, and then it bounces back up to maybe here, and then it's in the process of dropping, and eventually we have lots of different energy kind of going on here. What kind of energy did it have at the top? What kind of potential? Because was it chemical? No. What did we call it? I told one group yesterday. What kind of energy is it when an object has potential energy due to how high up it is? There you go.
Gravitational.
Gravitational potential energy. Gravitational potential energy. And as it falls, it's getting both. What two changes are happening to it? Physically, it's becoming lower. So what would we say is being reduced there? Is gravity being reduced? That would be wild. No. Its height is being reduced, right? Its height is going down. Its height is being reduced. I'm not going to say going down because that also the object is going down. Its height is being reduced. But what is increasing about it? Energy is never lost. Let's put that down. Energy is never created or on. Imagine if you had a smart science teacher. Or destroyed. But it does. What's the rest of that?
It's the law of conservation of energy. So it is
law of conservation of energy. But it does, okay, transform. Transform, the word trans, that prefix means across. It's going across forms, going from one form to another. Like a transvestite, someone who cross-dresses, or a transmission is a device in a vehicle that can cross energy or power from one part of the vehicle to another. Trans means cross, so it's crossing from one form to another. It does transform. In this case, it is transforming from, at the top, what we call, it had GPE. What might GPE stand for?
Gravitational energy.
Gravitational potential energy. Can you guess what the SI abbreviation for this might be when we do math with it, which is pretty soon? No, that's the unit.
Oh.
Nope. You won't guess. I'll just tell you. It's U. We use the symbol U to designate gravitational potential energy. So in this example from a lab that some of the students did, gravitational potential energy, U, is becoming what? Because it's not only lowering in height, and since energy can't be lost, that's what we were talking about. We were in the middle of talking about this when we switched to this. Since energy can't be lost, where's the energy going? It's not just getting, it's not, the energy itself is not getting lower, the object is. So what is increasing about it? Something must be going up if this is true, which it is. If energy can't be lost, as this kind of energy goes down, as this kind of energy reduces, what must be increasing, or what could be increasing? You can tell the potential energy is decreasing because it's reducing its height. Someone said it. Who was it? Nope. Nope. Gravity's staying the same. There you go. Its kinetic energy is increasing, and what would that look like? It's going what? Down, yes, but how is its motion changing? It is moving, but how is its motion changing? What do we call a change in motion, class? Acceleration. So if it's accelerating, it might be going. There are three kinds of acceleration. Which one is this doing? Faster. That's exactly it. It's going faster. So it's becoming, if its gravitational potential energy is decreasing because its height is being reduced, at the same time, its kinetic energy is increasing. What might KE stand for? Kinetic energy is increasing because it's going faster. Can you guess what abbreviation we might use for kinetic energy in the SI? Just K. So in this case, negating friction, what's the word negate mean? No? Yeah, not. We're forgetting friction. Negating friction, pretending friction doesn't exist, it is going from gravitational potential energy to kinetic energy as it lowers. Caden, would you hop up and in that top left drawer of my desk, you'll find, well, a lot of stuff, but I want a ball. Find me a ball from in there, please. So as this goes down, if it's here, right where we dropped it, I'm going to use a different color actually, sorry. If it's here, from right where we dropped it, what kind of energy does it have entirely? Okay, so as I hold it here, what kind of energy does it have? It has gravitational potential energy due to its what? Height. Okay, as I drop it, yeah, it slowly, well, I guess not very slowly, that's all relative, but it becomes kinetic energy. It gets faster and faster and faster. So as the height goes down, its gravitational potential energy becomes kinetic energy, and its height becomes speed, basically. Now let's think about, why don't you come up with the math terms that these will be based on? What do we know this has to depend on? We already said it. This must depend on gravity, lowercase g. What else must it depend on? Height, lowercase h. What else do you think it depends on? And I'll ask you this question so you can get it. Do you think this has more gravitational potential energy or something? This. Which one of these has more gravitational potential energy? Why? Yeah, because it's heavier, so it must have more mass. So that's the other thing it depends on. Let's come up with what do you think the kinetic energy is going to depend on? Mass, yes. What else? We said kinetic energy because it's going so fast. So how would we measure that in science? Yeah, almost. Come on. In between those. Velocity. There we go. So gravitational potential energy U depends on the gravity of the body, in this case the Earth, the height above that body, and the mass of the object. Here are the equations. U, I'm going to switch colors again. Remind me, what does U stand for? Yep. U equals mg GH, where U is gravitational potential energy, M is mass, and H is height. In the SI, how do we measure height? What unit? I'm sorry. Meters. Centimeters isn't wrong. It's just that for this math, meters is, it'll work out better. How do we measure mass in the SI? Kilograms. The base unit for mass is kilograms. We talked about how that can be confusing. And then how do we measure, oh, I'm sorry, I forgot a very important thing. G, sorry, little g, is oh, sorry, I should have asked you, what is G? Due to, accel due to gravity. I'll just abbreviate it. And how do we measure, I'm sorry, how do we measure acceleration in the SI? You remember. I know I'm having you cast your mind all the way back to last week, but you should probably remember this. What's the unit? Almost. Meters per second, or meters per second squared. Now check it out. If we multiply, since this is all multiplication, right? Kilogram times meter per second squared, we get a Newton. Remember that? Well, if we multiply that by a meter, we get a kilogram times a meter per second, sorry, meter squared per second squared. So kilogram times meter squared per second squared, which is equal to, you probably already know, what's a joule. A joule. So the unit for gravitational potential energy is a joule. I'm so glad I wrote it in green too. I'm so sorry. Let's do kinetic energy in yellow. Okay. S squared, second squared. No, I'll switch back to, no, I'm going to do it in yellow. No, I'm going to switch back to black. What the equation for kinetic energy is K equals, it does depend on the mass, and it does depend on the velocity, but it depends less on the mass than the velocity. So what it is 1/2 mv squared. So as velocity increases, if we double the velocity, what happens to the kinetic energy? If this was times 2, right, if there was a 2 here instead of a v, this would be 2 squared is 4. So if we double the velocity, the kinetic energy quadruples. It multiplies by 4. What if we triple the velocity?
It multiplies by 3.
Nope. This multiplies by, what's 3 squared? 9. So the more we increase the velocity, it not only increases the kinetic energy, but it increases squared. So again, we have K is kinetic energy. M is, come on, you can do it faster than this. M is mass measured in kilograms. V is velocity measured in, nope, just meters per second. But that does become squared, right? So if we squared both meters and second, what would we end up with in this? If we square this whole thing, we distribute the square, what do we end up with here? Meters squared per second squared. Thank you for saying that through a yawn. We end up with kilogram times meter squared per second squared, which guess what that is? Kilogram meter squared per second squared. Kilogram meter squared per second squared is I already told you, joule. So they're both measured in joules, even though we had different math to get there, right? This one was mass times acceleration due to gravity times height, and this one was only mass and velocity, but they both get measured in joules. Do you see some math? So we can measure kinetic energy, which is the energy due to, tell me, energy due to, I'm not just asking you. Class, kinetic energy is energy due to Energy an object has because of its,
Velocity.
okay, that's the way we measure it, but energy is due to its motion, thank you. And potential energy is energy an object has due to its,
Potential.
okay, yeah. We could, I'm going to put position, although that's not, if for all of them, it's not the very best thing, because like for chemical energy, it does have to do with the location of the atoms and the bonds. But let's go through another set of examples here. Wait, first, before that, do you have questions about this math? Do you think you could do this math?
No.
You don't. This is right out. You couldn't multiply three numbers by each other using a calculator. Eee. Yeah, you're right. That probably is going to be tricky. Good thing, practice makes perfect. And are you going to have an opportunity to practice this? I bet you are. Now, here's what might be kind of tricky. What might honestly be kind of tricky is that when we go to manipulate these, this is honestly, this is not hard at all. And this is not very hard, although the square might throw you off a little bit, but you're going to be okay. But when you start to manipulate them, it does get a little bit tricky, and so I'll help you with that. But that's something we'll just have to practice together. Now, I didn't get what I wanted from that. I asked you, do you think you can do this? And the answer is basically no, but I don't believe you. I don't think you believe in yourself. I think you can. Now, what are some kinds of energy? We have potential energy, which includes to us gravitational and chemical. We have electrical. What other kinds of energy are there? Mechanical. So mechanical is also both. And let me tell you the relationship between mechanical and thermal. Both of these are kinetic and potential. Both thermal and mechanical are kinetic and potential energy. The difference is, if I drop this ball, if I keep dropping the ball, when it's about here, pretend I'm dropping it, but when it's about here, does it have potential energy? Why don't you try to think about it and then answer right? How do you know it has potential energy? It has, yeah. What thing here does it, yes, have? Height. It does, you're right. It actually, all of them, but right now it has a height, a non-zero height. Does it have kinetic energy? Remember, pretend we've paused it. Yes, it has kinetic energy. You can tell because it's in movement. It's in movement. So as it falls, it has both kinetic and potential energy. And when we add those together, it has mechanical. And guess what? Negating friction, this does not change. So if we add its potential energy right here, okay, this is the top. How much potential energy does it have?
A lot.
Some, yeah. How much kinetic energy does it have? None. It hasn't started moving yet. So it's all potential. As it falls, it has both. And then right before it hits the ground, what's its height? Zero. It has zero height, so does it have potential energy? No. And it's moving as fast as it can before it hits the ground, and so it's all kinetic. So as the thing falls, it switches from potential to kinetic. In real life, that's mechanical energy, kinetic and potential. So mechanical energy doesn't change. However, in real life, there is friction, and there are some other things going on too. If what I just said were true, where could we expect, if it bounces perfectly, where would it come back up to? The same place, my hand. Does it? No. So some of that energy is being lost. Can energy be lost? No. So where's it going? Avery, I talked to you guys about this yesterday. Yeah. So some of it's becoming friction. So thermal energy, some of that energy is being dissipated into making the particles that make things up go faster. And that's what thermal energy is. So thermal energy is also kinetic and potential energy, but instead of being of a big object, it's of the individual little atoms or particles. Where else does that energy go? Sound. There you go. So sound is the movement of air particles. So the fact that we heard it means that some of that sound, some of that energy is being lost. Again, not actually lost. Nothing's ever created or destroyed. But some of it is being dissipated into the environment as sound. And where else does it go? Or where else could it go? If I drop instead my teacup, I'm not going to. Yeah, it'll break, right? And the energy will go to moving around the pieces that are left. I'm not going to do it because my grandma gave this to me. And I have tea in it, so it'd be a mess to clean up. But I almost got away with it. But if it breaks, that's energy lost. Again, not lost, but dissipated the environment. So we call that deformation, when a thing its substance gets broken up. If we had more time, we would talk about specific instances of energy transformation, of one kind of energy becoming another, but why don't you just give me some examples of that? Can you think of a time when electrical energy becomes sound energy? In what object would electrical energy become sound energy? Headphones, speakers, good. Can you think of a time when chemical energy would become electrical energy? No, because there is, hey, guess what, Trey? There's another thing called nuclear energy, so we could put that over here. Can you think of a time when chemical becomes electrical? No, probably not no, but that's not the best example. I'm thinking of a specific object that has chemical energy and it gives objects a battery. A battery changes chemical to electrical. And another one we could have, I'm hesitant to put this in either kinetic or potential, but I'm going to put it in kinetic. We have light. Can you think of an example of electrical energy becoming light? A light bulb. Yeah. So every change that has ever happened in the history of the universe has been energy. That's what energy does, is it changes things. Every change is energy, and energy is a way of measuring change. And so everything can be one of the, or there's more to these lists, but everything can be thought of as one of these becoming another. What does your body do primarily? What's its main job? Turning what to what kind of energy to what kind of energy? Chemical to? What do you do? Yeah, mechanical. Some of you, that's all you do is make sound. Bye.